Hey guys, this video is about the pH scale, strong acids and bases, and weak acids and bases. So we'll start out with the pH scale. The pH scale is a measure of acidity. It's a logarithmic scale. And the definition of pH is negative log base 10 of the concentration of hydronium, or remember that's the same thing as hydrogen ion. And the inverse of log is 10 to the minus, so, 10 to the log. So if we know the pH, if we're given the pH, then we can find the concentration of hydrogen ion in that solution by just taking 10 to the minus pH. If we're given the concentration of hydrogen ion or hydronium ion, just take negative log base 10 of that. Likewise, POH is defined in a similar manner. POH is negative log base 10 of the concentration of hydroxide ion, and if we know the POH, we can find the concentration of hydroxide by taking 10 to the minus POH. Now we know this over here. This is Kw, concentration of hydrogen ion or hydronium ion times the concentration of hydroxide equals 1.0 times 10 to the minus 14th at 25 Celsius, which is what we assume unless we're told otherwise. Which means that if we take the log of this and use the properties of logs, we see that that's equivalent to saying that pH plus POH equals 14.00. And that's good to 2 places past the decimal because this has 2 sig figs. And just remember from Chem 101, when you take any log of a number, any digits that you get to the left of the decimal do not count as sig figs because they're basically related to the power of 10. And so the sig figs, there's 2 here, so we have 2 past the decimal in our answer. So if we look at the pH scale, a pH of 7 is neutral because that means the concentration of hydrogen ion is 1 times 10 to the minus 7th. Any pH higher than that, so as you take the negative log of a smaller number, you get a larger result, is basic, and likewise any pH less than 7 is acidic. Now we can look at the scale, and it's good to be able to estimate pH or concentration of hydrogen ion without doing the actual calculation, although usually we'll do the calculation. So if this is always 1 times 10 to the minus something, if it's minus 1, then negative log of that is 1. Minus 2, it's 2, 3, 3, and so on. Which means that if we had, let's say, a concentration of hydrogen ion that was between 0.1 and 0.01, say a 0.095 or something like that, then we know, because the hydrogen ion concentration is between 0.1 and 0.1 and 0.01, we know that the pH is between 1 and 2, so it'll be 1 point something something. And that's just a good, way of estimating stuff to keep in your mind. Likewise, POH does the same thing, only it's sort of the inverse of pH. So if the concentration of hydroxide ion is less than 1 times 10 to the minus 7th, then that's a basic solution. Remember, if the hydrogen ion concentration was less than 1 times 10 to the minus 7th, it was acidic. It's just the inverse. And likewise, if the concentration of hydroxide ion is less than 1 times 10 to the minus 7th molar, then this is an acidic solution and the POH increases. So high pH means lower pH, low POH means higher pH. I hope I said that right. So, little example. What's the pH of a solution that is 0.000477 molar in hydroxide ion? Why don't you guys work this out real quick and come on back when you get an answer. Welcome back, guys. So there's a couple ways to do this. It's, you get the same exact answer if you take the concentration of hydroxide and find the concentration of hydrogen ion using Kw. We always assume we're at 25 Celsius unless told otherwise. The way I did it, I like to do it this way. I take the POH first because we're given hydroxide ion concentration, right? So I take negative log base 10 of that, and I get the POH, 3.3214. And then I just use this relationship here, POH plus POH equals 14.00, solve it for pH because I know POH, and I get 10.68. And we should always check and make sure our answer makes sense, right? Because this concentration is greater than 1 times 10 to the minus 7th, so we expect that to be a basic solution, which means it gives us a POH less than 7 and a pH greater than 7. And yeah, it does, so we're good. Okay, so strong acids. the 7 strong acids. Here they are. Memorize them for sure. Put them on your card. What it means for something to be a strong acid is that when in water, it completely dissociates into the hydrogen ion and the rest of the molecule, anion, the conjugate base. And because they do completely dissociate, the concentration of hydrogen ion or hydronium ion is exactly the same as the concentration of acid for a strong acid that's made up. So let's say we make a solution of nitric acid that's 0.123 molar, then we know that the concentration of hydrogen ion in that solution is 0.123 molar. And because we know the concentration of hydrogen ion, we can get the pH and so on. Now with sulfuric acid, this is the only diprotic polyprotic acid on this list here, and only the first proton is a strong, is a strong proton. It comes off completely. Both of these protons, the two H's here, are both acidic protons, but once the first one comes off, then the second one that's left behind there acts as a weak acid, which we'll talk about in a few minutes. Strong bases, likewise, completely dissociate in water into these all are all metal hydroxides, into hydroxide and the cation. And so that means that the concentration of hydroxide in a solution of any of these bases, there's 8 of them, is equal to the concentration of the compound we put in there. Unless it's one of these last 3, then it's twice, because there's 2 hydroxide ions for every one, forming a unit of calcium hydroxide, strontium hydroxide, and barium hydroxide. Now, calcium hydroxide and strontium hydroxide, if you go back and look at your solubility rules from Chem 101, you'll see they are listed as slightly soluble. But the thing is, guys, even though not very much of either of these compounds will dissolve in a given amount of water, whatever does dissolve stays completely dissociated. That's what makes it a strong base. Not necessarily that they dissolve easily in water, but the formula units that do dissociate do so completely. Barium hydroxide is kind of in between, but it does the same thing. The same amount of barium hydroxide, or however much barium hydroxide dissociates, does so completely and makes 2 hydroxides for every 1 barium hydroxide. So memorize these also, guys. So weak acids, Kas. So we listed 7 strong acids and 8 strong bases. If it's an acid and it's not one of those 7 strong acids, that means by default it's what we call a weak acid. Now, weak acids do not completely dissociate in water, meaning that there are still some molecules with an undissociated proton, the acidic proton, on them. So our generic weak acid equation is going to look like this. HA stands for proton and then acid, right? So an acid, and it dissociates some of them. Some of the molecules do to make hydronium ion. It's donating a proton to water, forming the hydronium ion, leaving behind the conjugate base of the weak acid. And exactly identical to this equation would just be, without the water, would be HA in equilibrium with H plus A minus. Same thing. You can write it either way. We do it both ways. So now we're back into the equilibrium stuff, guys. So the equilibrium expression for this reaction, because it is a heterogeneous equilibrium, where we do not include anything that's liquid or solid, which means the water, the H2O, does not appear. Everything else does. The equilibrium expression for this reaction will just be the concentration of hydronium times the concentration of the conjugate base over the concentration of the weak acid. We call that equilibrium constant Ka, A for acid. Right? So that's all it is. Ka is just the equilibrium constant for an acid. Now, just like we can do for pH and pOH, relating it to the concentration of hydrogen ion and hydroxide ion, we do the same thing for Kas. pKa is just defined as the negative log base 10 of the Ka, which means that if we know the pKa, we can get the Ka by taking 10 to the minus pKa. So that means, just like with pH, guys, pOH, the larger the Ka is, the lower, the smaller the pKa number will be, and the stronger the acid. Because if you look at this, right, the more hydronium ion or hydrogen ion there is at equilibrium, the stronger the acid, right? Well, that means the numerator, as we increase the value of the numerator by increasing the concentration of hydronium ion, which means because this is a 1-to-1 mole ratio over here, every one hydronium ion we make one of the conjugate base. So both of these guys increase as this equilibrium shifts farther and farther to the right. So the larger the value the numerator has and the smaller the value the denominator has, the larger the value this has, and that means larger Ka, stronger acid. More of that molecule is dissociated into hydronium ion and conjugate base at equilibrium. And because of the way that this definition of pKa works, just like pH, the larger the value of Ka, the stronger the acid. The lower the value of the pKa, the stronger the acid. And these are just some examples over here. There's way more acids than this. This goes from, these are all weak acids. They go from strong to weaker, stronger weak acids, I guess, to weaker weak acids. Now, okay, so the definition, okay, of what makes something, let's back up a second here, because this is important to know. What makes something a strong acid is that it's a stronger acid than the hydronium ion. In other words, it has a Ka greater than 1. And so if we look at over here, so that's something to keep in mind. Now, if we look at these, right, so this is the Ka for chloroacetic acid is 5.6 times 10 to the minus 2. The Ka for phenol is 1.3 times 10 to the minus 10th. This is a much smaller number than this because this is a larger Ka. We see this is a stronger weak acid than phenol, which is a weaker weak acid than chloroacetic. Now let's look at these two guys right here, chloroacetic as opposed to hydrofluoric acid. We know that, let's just look at hydrofluoric acid. So we see that its Ka is 7.1 times 10 to the minus 4. Well, if it was 1 times 10 to the minus 4th, its pKa would be 4, right? Just like with pH. But this is larger than that. This is going to have a pKa between 4 and 5. So we know it's going to be 4 point something something. If we need to know those two past the decimal, we can always do the calculation. All right, so those are that. So if we know Ka or pKa, because if we know pKa, that means we know Ka, we can calculate the pH. Because calculating pH, because pH is defined as the negative log of the concentration of hydrogen ion, it means finding the concentration of hydrogen ion and then just taking the negative log base 10 of that. Well, this is an equilibrium problem, just like we did back in the equilibrium module. And we're going to keep doing equilibrium problems for a while. So we're going to set up an ice table, everybody's favorite. So here's an example for you guys to try out. Calculate the pH of a solution whose initial concentration of acetic acid, there's the formula for acetic acid, is 0.454 molar. And I give you the pKa for acetic acid, 4.747. All right, so why don't you guys go ahead and give this a shot and come on back when you finish. Welcome back, guys. Here we go. So I set up an ice table. So there's our generic equilibrium. I just wrote it as HA. It doesn't really matter what the formula is. We know that it's a monoprotic weak acid. And so it loses a proton. Okay, this is equivalent to plus water and hydronium over here, like I showed you earlier. And so our initial concentration, we're told, is 0.454 molar, and we don't have any hydrogen ion or conjugate base acetate. And so that means we're going to, because these are all coefficients of 1, makes it easy, right? Minus x here, plus x here, plus x here. At equilibrium, we have 0.454 minus x of acetic acid, and x of hydrogen ion, and x of acetate ion. Now we're given the pKa, so let's make this all blue. So if we're given the pKa as 4.747, so we're going to need the equilibrium constant to do our equilibrium calculation. So we take 10 to the minus pKa, and we get 1.79 times 10 to the minus 5th. Again, sig figs, guys. Because we know that a pKa came from taking the log, negative log of a number, we know that the digit to the left of the decimal, the 4 in this case, is not a sig fig. So the pKa only has 3 sig figs, the 7, 4, and 7. And so we only have 3 sig figs for our Ka. All right, so now from our ice table, we see that Ka, the equilibrium constant, is equal to x squared over 0.454 minus x. Now, a couple things, guys. For a weak acid, as long as we don't initially put any hydrogen ion or conjugate base in the solution, which we can do, but if there's none of that to start with, it's always going to look like this, x squared over the initial concentration minus x. So we get to a point where we don't really have to even write out the ice table. But we wrote it out for here so you can see it. Now, we're going to try to make the approximation that x is a lot less than 0.454. And it seems reasonable because this is a fairly small Ka, equilibrium constant. So if it is, we get x squared over 0.454, and we don't even have to solve a quadratic. We just multiply through by 0.454, take the square root, and there you go, we got our x. And so we get, doing it that way, we get x is 0.002851 molar. And if you do solve the full quadratic, you get x is 0.00284. Much less, it's less than 5% of the initial concentration, much less. And so it's a good approximation. Real quick, guys, on the exams, you will always, just like with equilibrium, you will always be able to do this. As a matter of fact, you should always do this. You see, right, you get a slightly different answer solving the full quadratic. Don't on an exam, because then you might be tempted to pick none of the above, and that's not what you want to do. I always use the number that you get by neglecting x, and so you guys should too on exams. All right, so now that we know x, we see that x is equal to the concentration of hydrogen ion at equilibrium, and so that means that now we can get the pH, which is what we wanted, negative log base 10 of the concentration of hydrogen ion. And so we plugged it in, and we get 2.545 for the pH. There we go. Percent ionization. So percent ionization, it's really just like the 5% rule. It's just the concentration of hydrogen ion at equilibrium divided by the initial concentration of the weak acid times 100. And the thing about hydrogen ion, percent ionization is that as we start with higher and higher concentrations of the acid, the percent ionization decreases. Now, that doesn't mean the amount of hydrogen ion decreases. As we start with more, we end up with more hydrogen ion as we start with a greater initial concentration of our acid, we end up with more hydrogen ion in solution. But the percent that ionizes decreases, just like this. So if we look at our previous example with the acetic acid, we can calculate the percent ionization real easily. Remember, our initial concentration was 0.454 molar, and we calculated the concentration of hydrogen ion at equilibrium was 0.00285 molar. Divide the two, multiply by 100, and we get 0.628%. Now, it's also possible, we do this, if we're given percent ionization, to calculate things like Ka. Because if we know what number this is equal to, and we know what, and of course we have to be given the initial concentration, then we can solve for the hydrogen ion concentration at equilibrium, which means we know x in x squared over the initial concentration minus x, and we can just plug in. Watch. So we're told that for a certain weak acid, its percent ionization, when you start out with initial concentration of 0.328 molar of this weak acid, the percent ionization is 1.98%. What is Ka for this weak acid? Go ahead and work it out, guys, and come on back when you get your answer. Welcome back, guys. Here we go. So start out with the definition of percent ionization, and like I was trying to explain a minute ago, just rearrange this guy. So pull this guy up here, divide by 100, and we solve for the concentration of hydrogen ion at equilibrium. It's equal to the percent ionization times the initial concentration of the acid over 100. So we were told that it was 1.9% ionized, so 1.98 times the initial concentration over 100 tells us the hydrogen ion concentration, 0.00649 molar. That's our x in our x squared over the initial concentration minus x, right? Remember, Ka. So we know x, we can plug in, and we get 1.31 times 10 to the minus fourth for Ka. Now, it's true. This value is much smaller than this, and we could have neglected this. And when we do it ends up, you get like 1.29, I think, times 10 to the minus fourth. But in this case, there's no rationalization for neglecting it because it's so easy to plug in. So don't do that. Just go ahead and plug it in here. The reason why we neglect x when we're doing sort of the other way around is that it makes it easier to solve the quadratic. It doesn't do anything for us here. All right, so going on. Weak bases, Kb and pKb. Just exactly analogous to weak acids, Ka and pKa. So we know that 8 strong bases, if it's a base and it's not one of those, then it's a weak base. And weak bases don't completely dissociate in water, but rather there is an equilibrium. Now, you should get used to this, guys. A real common type of base, not the only one, of weak base is what it's called an amine. And this is going to be some compound that ends in nitrogen with 0, 1, or 2 hydrogens on it. So ethylamine, methylamine, ammonia, NH3, pyridine, that has nitrogen, no hydrogens on it, aniline, urea. These are just examples. There are literally thousands of them. But the equilibrium reaction for a weak base looks like this. B stands for base, and so we think about it as accepting a proton from water, which is now acting as an acid, forming BH plus, the conjugate acid of the base, leaving behind hydroxide. Now, this is a generic base. If this already has a charge on it, it just has one more positive charge. If this has a negative charge to start with, it'll have a 0 charge over here and so on. But Kb looks a lot like Ka, except that it's the conjugate acid times hydroxide over the initial concentration of the base. And this is called the base ionization constant. And I didn't show it here, but just like with Ka, pKb is negative log base 10 of Kb, and Kb is 10 to the minus pKb. It works exactly the same. And so we see here, and just like with an acid, the larger the Kb, the lower the pKb, the stronger the base. So look at these guys right here. Ethylamine is a slightly stronger base than methylamine because 5.6 times 10 to the minus fourth is a little bit bigger than 4.4 times 10 to the minus fourth, but those are both bigger than 1.8 times 10 to the minus fifth, and as we go down, we get weaker and weaker and weaker. Okay, so calculating pH from Kb and pKb. So usually we talk about pH instead of pOH because it's just kind of the accepted, it's more commonly used, so that's why we do this. So if we're given the Kb or pKb and the initial concentration, then we can find the hydroxide ion concentration and consequently the hydrogen ion concentration, and that means pH. And to do this, it's an equilibrium problem, so we can set up an ice table. So here we go. We want to calculate the pH. It means we need to come up with the concentration of hydrogen ion, or pOH, and then we can find pH, whose initial concentration of ethylamine, that's the base, is 0.0519 molar, and we're given the pKb of ethylamine. That means that Kb is 10 to the minus fifth. So why don't you guys go ahead and work this out, get an answer, come on back. Welcome back, guys. So here's what our equilibrium looks like. There's our base, there's water. Base accepts a proton, so now it has a plus charge because it started out with a 0 charge. And ethyl ammonium ion is what this is called, and hydroxide. And so typical ice table, initial 0, 0, minus x plus x, equilibrium minus x, so we get x squared over 0.059 minus x. Now guys, just a word of warning, watch out. We get so used to, because we start with pKa's and Ka's and acids, we get used to x meaning being the same as the concentration of hydrogen ion at equilibrium, but you have to be careful about what equilibrium you're speaking of. Here, because x is not equal to the hydrogen ion, but rather hydroxide, we just have to keep that in mind, that's all. But anyway, so we're given the pKb, so 10 to the minus pKb is our Kb. Again, 2 sig figs, 5.6 times 10 to the minus fourth. We know Kb, we know that equilibrium expression is x squared over 0.059 minus x. Solve this. Now, here, we have to be careful. if we make the assumption that x is a lot less than 0.0519, it ends up not being a good assumption. And it's still a good thing to do because it's so quick. Just do it. Like, oh, I pretty much always do that and then go back and check. So what I did is I said, all right, what if x is a lot less than this? That means it's real easy. I just plug this in for kb, multiply kb times 0.0519, take the square root, and I got x is 0.00540 molar. Then when I took this and divided by 0.0519 times 100, I say, uh-oh, that's like 10%. That definitely doesn't satisfy the 5% rule. It's all right, no big deal. Go back, I solved the full quadratic, and I got my x. Well, we got x, right? Remember, we want the pH, right? X is equal to the concentration of hydroxide. Now, when you guys get to this point, you have a couple of choices. You could either use the Kw expression to find the hydrogen ion concentration. You know, we always assume 25 Celsius. And then once you get hydrogen ion concentration, just take negative log base 10 of that, and you got it. You'll get, try it, you'll get exactly the same answer. I like to do it this way, just, I don't know, seems easier. They're both easy. Is I find my POH, negative log base 10 of my hydroxide ion concentration, and then all I do is subtract that from 14.00, and I get my pH is 11.71. And again, we want to make sure this makes sense, right? This is a base, so we expect the solution to be basic, meaning the pH greater than 7, yep. POH less than 7, yep. So we're good. And that's all there is to that, guys.